Mary Leng, are numbers real?
No, they're no more real than Sherlock Holmes.
Well, I think our viewers and listeners are going to want some explanation, some justification of that wild claim you just made. But so maybe we can back up a little bit, though, to start off with. So, Mary, you're a distinguished philosopher of mathematics. And I'm not sure how much our viewers or listeners know about philosophy of mathematics. So let's just start with the basics. People might be thinking, what is philosophy of mathematics and why do we need it? Aren't mathematicians doing perfectly well anyway without philosophers giving them a hand?
Yes, they are, because mathematicians generally aren't asking philosophical questions about mathematics. They're doing mathematics. But any successful discipline is worth our attention and worth looking at. And in the case of mathematics, we think, well, look, there's mathematicians going about proving theorems, doing what they're doing. It turns out what they do is incredibly useful for science. It turns out that what they're doing has insight in its own right. Can we understand what's going on in that practice? And as a philosopher, I look at that from the perspective of a philosopher who's interested in metaphysics, what there is, and epistemology, how we know it.
Right.
So in relation to mathematics, mathematicians don't themselves have to worry very much about this, but I'm interested in the question, well, what is a number? Mathematicians talk about numbers. What are these things? And depending on what we say about what numbers are, how do we know about them? How is it that the methods that mathematicians use are so well suited to finding out about these things?
Yes, I suppose in mathematics we seem to be talking about certain entities, numbers, the number 9, and they don't seem to be the sort of things you bump into walking around the spatio-temporal world. Where's the number 9? And so is that a core philosophical issue in the philosophy of maths? What are numbers? Where are they? What kind of entities are they?
Absolutely, because we're all so familiar with the numbers. We learn about them from a very young age. And in fact, the knowledge we have about the numbers seems to have this special character, right? It seems that, I can be absolutely certain that 2 + 2 = 4 in a way that hardly anything else comes close, right? So that raises an interesting question. What are these things that we can know about them with such certainty? But when we start looking at the kinds of things that numbers could be, it's very difficult then to provide an answer that does allow for us to make sense of the idea that we can know them so well,
right,
and with such certainty. Because, well, if we try and say what numbers are, the answers people typically give involve saying what they're not, right? So the number 9, as you said, it's not something we walk around and bump into. It's not spatio-temporally located. It's not physically there in the world. So people say, well, okay, so it's not spatio-temporal, it's not physical. Maybe it's a mental object. Maybe it's something like an idea in my mind, right? But then one difficulty with that is the kind of objectivity of truths about the numbers. So if I had my number 9 and you had your number 9 and we just talked about our own ideas, that wouldn't give the right kind of objectivity that we think that mathematics has. Also, when we start looking into mathematical objects and numbers, it's not just that the number 9, the number 10, and so on. It's all the numbers, and
yes.
Whose head's big enough to hold all of those?
Not mine.
Mine neither. So the idea that a number's somehow an idea in our heads doesn't seem to work. So it doesn't seem to be a mental kind of object. Sometimes people say, well, maybe the numbers they're kind of linguistic. They're somehow related to the names we have or the parts of language we have. But again, once we go into advanced mathematics, the theory says there's more mathematical objects than could ever be written down in a finite language. So that's not going to really help. So we have these kind of false starts at trying to think, well, what kind of things could they be? And the answers that people tend to give are these negative ones. They're not mental, they're not spatiotemporal, they're not causal, they're not linguistic, they're not social constructs or whatever. All of those answers, when you start going into them, they all have problems. And so the answers that philosophers typically come to is to say, well, they're none of those, none of the above, and there's a label we use for that. We say they're abstract. So abstract as I'm presenting it, is kind of characterised in this negative way. None of those other things. So we've got this idea of numbers as existing, as abstract, as in none of the above, none of those things. And as soon as we make that move, the problem of knowledge comes in, right? Because once we've said they're not this, they're not that, they're not the other, we block off most of our usual ways of understanding how we could know about them, right? So if we've said they're not spatiotemporal, we can't know about them through our spatiotemporal interactions in the same way that we know about the objects, the physical objects in the world, right? Soon as we say they're not mental, we can't know about them but through reflecting on our own ideas in our heads, and so on and so on. So all of these negative characterizations of numbers kind of block off the usual ways that we have for explaining how we can come to know about these things. And there looks to be a big gap. What can we say positively about how we can know about objects of that sort that don't satisfy any of the standard criteria for things we can know about?
Right, so that makes a lot of sense. I mean, would it be useful to connect this to Plato, right, from history? I guess he's the person we most associate with this idea that numbers are real entities, but completely separate from space and time. They have their own existence outside of the spatio-temporal world. So I guess this is the view that's commonly called Platonism, in honor of Plato. And it's a fairly popular view, right? Platonism.
Yeah, absolutely.
This is not your own view, as we'll get to, but it's...
So I would say the mainstream of philosophy of mathematics takes it that Platonism of some form is correct.
Right.
In the sense of saying, yes, numbers exist and numbers are abstract. Now...
So mainstream in philosophy and in mathematics, among mathematicians, or what?
It's very hard to know amongst mathematicians. I think mathematicians have different... as much a range of approaches as philosophers. Some people will say, well, look, if you just look at what mathematicians say, it's clear that they're Platonists, because mathematicians will say there are infinitely many prime numbers. We've proved it. Right, and if you say there are infinitely many prime numbers... If you take that at face
value, they are saying these
things exist, right? They're not questioning or worrying about that. No one's looking at the proof that's been around since antiquity and saying, well, do we really know there are these things? As it's from a mathematical perspective, it's as certain as can be that there are infinitely many prime numbers.
Right.
So on the face of it, it looks like mathematicians are Platonists. If you kind of scratch the surface, different mathematicians will express different views. They're not professional philosoers.
We'll forgive them.
So some mathematicians have quite sophisticated views, some have less. So some will be quite happy to say, well, somehow they're really just ideas or whatever. I don't think it's helpful as philosophers to try and work out what mathematicians really think about those philosophical questions. What we do need to do, though, as philosophers, is to make sense of their practice.
Right.
Why is it okay as a mathematician to say, absolutely, there are infinitely many prime numbers, full stop, don't worry anymore.
Right.
So any philosophical account that said there was something wrong with that, I think we ought to start worrying.
That makes sense. So we're not telling them what to do, but we're trying to... What do we need to believe to make sense of what they're doing?
Exactly.
So we've got the Plato's view that these are entities outside of space and time, and as you say, Mary, that the initial problem is how the hell do we know about these things? By what special faculty do we connect to these things outside of space and time? I mean, and Plato had an answer, right?
Yeah,
Plato had an answer.
Although, as I've said, very many philosophers of mathematics would call themselves Platonists. Not very many have followed Plato in the epistemology. So Plato's idea is that, well, before we were embodied in the world, our souls were up there in Plato's heaven communing directly with the forms, and that's how we know about numbers and abstract things. And when we're here in the world, we recollect that knowledge and that
So
that direct acquaintance.
Is this the famous? Is it which dialogue is it now with the slave boy and he teaches mathematics to the slave boy?
Exactly, and
the slave boy is remembering.
Yes, and Plato's idea is, look, it must have been all along because he can work this stuff out.
We hung out with the numbers before we were born.
Yeah, that's the only explanation of it.
But
so,
yeah,
it's fair play. If you're going to have that kind of account of what mathematics is about, it gives you a story as to how we could come to know these things. But it's not a story that most contemporary philosophers.
So Platonism is a popular view, but most people aren't going to go along with Plato's explanation of how we know about these things. Exactly. And then the question is, well, how the hell do we know about them?
So what are you going to say about them?
What do Platonists say? Do they have answers on this?
There's a range. So one answer that's relatively popular is to say, well, come on, we know about these objects the same way as we know about any of the theoretical entities of science, right? We don't directly interact with electrons, but they're part of our best explanations of our observation. And mathematical objects are right there in our best scientific theories, right? So we know that there must be these things because they're part of our best theoretical explanation of what the world is like.
Theoretical posits kind of thing, in a way that mathematics involves, physics involves mathematics, and so we should think of them as theoretical posits like particles.
Exactly.
That's pretty good. What's wrong with that?
Well, a couple of things. So one worry there is it doesn't seem to get the epistemology right from a perspective of the mathematician and mathematical experience. Right? So one thing we started with was the thought that actually the basic truths of arithmetic are things that we just all know with absolute certainty. Now, on this picture, it turns out that the existence of numbers is a highly theoretical posit that's part of, as it turns out, we might have to posit numbers to express our scientific theories. If we do have to posit numbers to express our scientific theories, then we ought to believe that there are numbers and that claims like 2 + 2 = 4 are true of them. That doesn't seem to ring true to the way we seem to feel that we know mathematical claims. So that's one worry.
So we're not sort of dependent on what the scientists say. It's not like we're waiting on scientists will change their mind and say, oh, actually, the number 9 doesn't exist in the way we would be with, if physicists tell us space and time don't exist at the fundamental level, we're prepared to follow them in that. But mathematical claims don't seem to be so dependent on the latest scientific discoveries.
Exactly. Cool. So that's one worry. Another worry really comes about thinking about scientific confirmation. So the thought is that, this argument goes, look, numbers get confirmed by their role in science just like electrons do. But of course, numbers play quite a different role in science from electrons. So part of our reason for believing in things like electrons is their role in causal explanations of observation.
Right.
That track in the cloud chamber was caused by something going on at the subatomic level, or at the unobservable level. Numbers, although they make their way into our scientific theories, they don't appear in those kinds of causal explanations, and so people like me who doubt this argument will start looking at what it is that numbers are actually doing in our scientific theories. And it seems that in our scientific theories we are trying to produce models to describe the observations that we see. Mathematics makes its way into these models that describe, but we can give an account of how a model could be used to describe the world that explains how the model tells us things about what the world is like, but doesn't require us to think that the objects in the model really exist in any way.
Right.
So, much like when I say, that detective's really hot, he's just like Sherlock Holmes, he'll get the answer. I've used Holmes's properties to predict how the detective is going to be because he's like Sherlock Holmes in having certain mental faculties and so on. But that doesn't mean I have to believe in Sherlock Holmes, right?
I see. Right.
So this story of how mathematics gets applied raises the question then, well, if mathematics is being used in that kind of way to help kind of build models to describe the physical world and make predictions about the physical world, do we have to believe in the objects in those models, the mathematical objects? And lots of people, myself included, try to offer a story of how that kind of use of mathematics can work that doesn't require us to believe that there are mathematical objects.
So this sounds to me actually connected. Is this connected to the indispensability
Absolutely,
argument?
yes,
So this is one of the arguments Platonists, among others, might use for saying, look, we need to believe in numbers. It's not just that it seems to be reflected in some mathematical talk or they seem intuitive or something, but they're an indispensable part of our best scientific theories. So we really need to believe in these things. Now, actually, some opponents of Platonism, Hartree-Field, I think most famously, tries to say, well, in principle, we could do without mathematical entities in our theories, which sounds sort of bizarre. So what, does he have a version of Newtonian mechanics or something without mathematics?
Absolutely, yeah.
Which sounds bizarre when you tell people. You tell us a little bit about that, because it's so interesting.
So this argument, as you say, this so-called indispensability argument is meant to be an argument against people like me who say, look, maths is just a useful fiction. And the argument goes, look, science is true. We've got reason to believe our scientific theories. Mathematics is indispensable to our scientific theories. You can't even state the laws that you use to express your scientific theories without giving equations, right?
Yes.
You're using numbers, functions.
Right.
So if you believe science is true, we're all scientific realists, right? If you believe science is true, or even if you believe you've got good reason to believe science is true until something better comes along, any of those kind of broadly realist approaches to science get you mathematical realism with them, and therefore mathematical objects, mathematical Platonism. So if you don't believe in numbers, if you think numbers are a kind of useful fiction, you need to respond to that argument.
Yes.
And there's been two broad strategies of responding, which get called the easy road and the hard road in mathematical fictionalism. So the version you mentioned, Hartree-Field, is what's known as the hard road of responding
I can see why that adjective applies. If you're going to say we can give science without any mathematics, that sounds pretty hard.
So this approach says, we're standard scientific realists. We believe our scientific theories are true.
Yes.
Our best scientific theories.
Should we just say what scientific realism is, just in case people don't know?
Sure. So there's typically three components, if I can remember off the top of my head, the so-called Putnam-Boyd formulation of scientific realism, which says, so when we're giving our scientific theories, we think that the terms in those scientific theories typically refer to objects. So the aim of, when we're talking about electrons, the aim of, in doing science, we're attempting to talk about objects. We're not just using electron talk as a useful instrument, as a way to predict observations. So that's one way of avoiding a certain scientific anti-realism, which says, look, we shouldn't take our scientific discourse literally. When scientists are talking about electrons, they're just using that as a useful tool to help move from one observation to another observation.
Yes.
So the first component says, no, take your scientific theories at face value. When scientists are talking about electrons, they're not doing that as a merely useful tool. They're aiming to talk about objects. So the terms are aiming to refer to things we should give a face value reading.
Right, so this is a good analogy, isn't it? I had a much discussed Twitter argument with the physicist Sabine Hossenfelder over whether electrons exist over this. Yeah. And it was quite funny, actually. Lots of people were wading in, and they all thought it was the philosopher saying electrons don't exist. And everyone was saying, oh, you stupid philosophers, what are you on about? And so I'm sorry, you're on my side of this. There's about 3 articles written on it. So it was a good way of introducing people to this realism, anti-realism debate. So actually, maybe this might be a good way of connecting to what we're talking about. So the normal, as it were, realism, anti-realism debate might be, are electrons real? Or are they just a useful fiction for using science as a sort of predictive tool?
Okay, it's a bridge to get from observation to prediction, observation to prediction. Throw in this scientific machinery, and that allows you to input your observations, export a prediction.
Right. And then
the realist about science says, we're doing more than that. When we're using the science, we're trying to talk about what's really going on. We're not just using electron talk as a useful tool, we're using it as an account of what the world's like.
Okay, so that's familiar realism. Actually, Sabina's blocked me on Twitter now, so that was anyway. Right, but so that's are electrons real, or are they used for fiction? And then what you're into, what we're discussing here, is sort of is it analogously applying that to the mathematical entities that seem, in some sense, to pop up in science?
Exactly. So just to say a little bit more about what's involved in the realism debate, the first is a claim about the semantics, the meaning of our scientific terms. So electron means electron. It's an object term. It's not just a useful instrument. But the second is a claim that it's an epistemic claim. It's a claim that we have reason to believe that our best scientific theories are getting things right. So there can be anti-realists about science who say, yeah, sure, when scientists are using terms like electron, they're not using it in this merely instrumental way. They're trying to talk about objects, but they're just mistaken about that, right? There aren't really electrons. They've got things wrong. We don't have good reason for believing our scientific theory is true. So the second component of realism is to say, not only are we aiming to talk about electrons, we have good reason for believing, not that our theories have got things absolutely right, but objects something like that exist there in the world.
Yes.
And of course, when we start looking at what our theories really say about electrons, our picture of them as kind of tiny point particles might disappear. We might think, it's much more complicated than that. But nevertheless, the thought is, okay, we've got some good reason for believing that objects exist in the world that's answer to many of the things that our theories are talking about.
I see. Right.
Okay,
Good.
So on to numbers then. So if we've bought scientific realism in that sense, our best scientific theories are to be read at face value. When they say there is an electron, we believe that there are electrons. They mean there are electrons. And secondly, that we've got reason to believe that they're true. So when they say there are electrons, we've got reason to believe that that is correct. If we take that picture and then find that our scientific theories are talking about mathematical objects all the way through, then we ought to, just coherence, intellectual honesty requires us to say, yeah, okay, I believe in electrons, so I believe in numbers too, or functions, real numbers, functions, all of those things that are there in our scientific theories. So
it's sort of applying the same consistent methodology.
If you're a scientific realist, and if this is what you mean by scientific realism,
if we're going to believe in electrons,
you've got to have numbers.
We should believe in numbers too.
Yeah. So if you don't believe in numbers, you have to find some way of responding to that argument. And this is where we get to the easy and the hard road. So the hard road, Hartree-Field's approach, is to say, well, look, I'm a scientific realist about my best scientific theories. I believe our best scientific theories are true or approximately true, and they should be read at face value. Shouldn't you believe in numbers then? No, he says, because our best scientific theories, the ones that are really getting at what's going on in the world, are ones that are not formulated mathematically. The mathematical formulations are a kind of convenient way of expressing our best theories about the world. But we can rewrite those theories in ways that don't, in their basic laws, refer to numbers at all. So that's the hard road, because it requires a lot of work, right? You have to work out how to reformulate your best scientific theories so that they're no longer talking about real numbers. And, numbers get in as soon as you measure something, right? If I say, okay, this distance is d centimetres, okay, I've talked about 30 centimetres, I've talked about the number 30, right? How are we going to do that? Well, actually, if you're ingenious enough, there are ways of making those kinds of claims.
Really? So how on earth do we do that? So Field wants to say, okay, we use mathematics because it's kind of convenient, but in principle, you could do science, articulate it without any mathematics. So how would you do that? How would you even begin to do that?
Just before I begin to do that, one clarification about Field. He doesn't think that we could do science without numbers, really. Even though his book's called Science Without Numbers, he doesn't think we could do science without numbers.
Right.
Really, practically, we're going to have to use numbers. But what he does think is we can express the basic laws of our scientific theories without numbers. Once we've expressed them without numbers, we can then explain how, if that's what we think is true, adding mathematics to that is going to be trustworthy, is going to allow us to get from true claims to true claims, even if we don't believe the maths is true.
Right.
So we are going to use maths eventually, but not on day one of writing down what our scientific laws are. So we write down the scientific laws, and then we get permission for expressing those in mathematical terms and using the maths as a kind of useful instrument.
All right, so just give us some sense of how we can frame these claims without mathematics, like 30 centimetres.
Okay, so I'm not going to give you all the laws of Newtonian science, but or any scientific theory. But let's just go to basics. Using numbers to measure distances in the world. So this length is 30 centimetres. There, it's convenient to use the numbers, but of course, what I'm really saying about that length is something about its relation to a unit, right?
Right.
So I've got here's my 1 centimetre distance, or whatever my standard unit's going to be. I'm going to say, okay, let's take the distance here between these space-time points. And Field takes a basic ontology of space-time points and space-time regions. So we've got 2 space-time points here, and we can say, okay, there's a distance between them. Field's basic idea is to talk about congruence between distances. So instead of saying this and this and this and this are all related to the real number 1 centimetre, by the distance in centimetre function, he says, no, this distance and this distance and this distance and this distance are all distant congruent to each other. I.e., if you put them end to end,
right,
they'd be the same. So he has as his basic, instead of having functions from physical lengths to real numbers, his basic idea is the idea of congruence in distance, or congruence in mass, or congruence in all these other measurable properties. So this distance is distant congruent to this distance. Now, my 30 centimetre distance isn't distant congruence to this or to this, but it is congruent to 30 copies of this. You think, oh, there's that number 30. It's coming. But...
Can't get rid of it. It's like whack-a-mole.
But that's okay, because actually, as you'll know as a philosopher who's done a bit of logic, if I just want to say there are 30 things, I don't need to appeal to the number 30. I can say there's a thing and another thing and another thing and another thing and blah, 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 and they're all different from each other.
Right.
So I can effectively say that this distance is distant congruent to 30 copies of these without using the number 30. It's going to be a long, complicated thing to say, but I can say it. Now, that's a very basic formulation of the basic idea. And in order to show that, so in Field's book, Science Without Numbers, he shows that if you help yourself to these congruence relations and an ontology of space-time points, you can express the laws of Newtonian science using just these things. He makes use of the mathematical theory of measurement theory to explain how that can be done, or to justify how that can be done. He then says, okay, well, that's sketched how at least one scientific theory could be expressed in non-mathematical terms. Once we've got that expression, we can say, that's the theory I believe when I'm doing science. And you'll say, well, but when you're doing science, actually you use all these mathematical theories. That's not the theory you use when you're doing science. And that's where the second component of Field's program comes in, because then he says, look, I can show you, I can prove that mathematics has a wonderful property, a property called conservativeness. And what it means to say mathematics is conservative is that if you start with a body of claims that are entirely non-mathematical, so such as the laws of our newly written scientific theory, our newly written version of scientific theory, if you start with a body of claims like that, and then you combine them with mathematics, you add mathematics to that, nothing that you can prove about the non-mathematical stuff, no nominalistic claims that you can prove with the added mathematics, didn't already follow from the nominalistic claims you started with. I see. The non-mathematical claims you started with. So in that way, Field's account of how maths gets used in science is truly instrumental. right? He shows how, if that's the theory you started with, this is just going to be a really useful tool that allows you to get from non-mathematical claims to non-mathematical claims. So you can get your observation in non-mathematical terms, express it in that way, add your non-mathematical theory, which has the laws of your scientific theory, those two things together, and add in a bunch of mathematics, churn the wheel, churn out your results, get some non-mathematical conclusions out of that, and what you'll know is, regardless of whether the mathematics was true, so long as it has this property of conservativeness, nothing that you get wasn't already a consequence of the non-mathematical claims that you started with.
Okay, so that's the hard road, and it's basically saying, these are attempts to respond to this indispensability argument that mathematics, numbers is indispensable to science. Field says, actually, no, it's not. We can kind of get rid of it, to oversimplify. You've given some nuance there. So that's given me a headache. What's the easy road? So the easy road is saying, maybe it's indispensable, but we still don't have to believe in numbers. Can you tell us?
Exactly. So
I like the word easy.
So the easy road
Go for it.
Feels that, this is a load of hard work trying to rewrite our scientific theories in non-mathematical terms, and we're not clear that we can do that for all the theories. So Field sketches an approach for Newtonian theory. Can we do it? Lots of people have tried. There's certainly been progress. So one of the issues was, can we do quantum mechanics this way? There's been lots of progress in giving nominalistic theory. So it might not be impossible, but the easy road nominalists say, well, hold on a minute. All of that project was predicated on the thought that we have to believe our best scientific theories are true. But what Field shows is, if these nominalistic theories are our best scientific theories, then we can be immensely successful with mathematical versions of those theories, even though those mathematical versions are not true. Then Easy Roader says, well, hold on a minute. That shows that successful theories don't always have to be true to be successful, right? So do we really have to believe our best scientific theories are true if they turn out to be these mathematical theories and not nominalistic versions? Well, obviously we can't use Field's technical project to give his story about why those theories are successful, but we can, I think, do something similar. We can kind of lean on Field's project to say, well, why in Field's picture are mathematically stated scientific theories successful? It's not because they're true, it's because they include a true nominalistic theory, and the mathematical add-ons to that don't make any don't conflict with the true nominalistic facts.
Right.
Now,
so nominalism means not referring to numbers.
In this context,
Yeah.
So obviously nominalism means lots of things to lots of people. In this context, we're using nominalistic claims to be claims that aren't talking about mathematical objects. No quantifying over numbers or functions or sets and so on.
I see.
So the easy roaders say, well, look, Field's approach requires us to express that so-called nominalistic content of our scientific theories in non-mathematical terms to give this technical explanation of how the mathematical theory is successful. We think that we might not be able to express the so-called nominalistic content of our scientific theories in purely non-mathematical terms. There might be things that we want to say that are really about the concrete world, but we can only say them by helping ourselves to mathematical objects. So, to take an example, if I can think of one quickly, suppose that I want to say that suppose it turns out that space-time is infinite, continuous, structured the way the real numbers are. Is it going to be easy to say that without reference to the real numbers? Well, yeah, maybe I could do it in a hard way, give you a Fields program. But if I say space-time is structured like the real numbers, really that's a claim about the structure of space-time rather than about these real numbers. Right? So yeah, maybe I could somehow find a really tortuous way of saying that without talking about the real numbers, but that's hard to do and not always necessarily possible to do. And yet, what the numbers are doing there is clearly allowing me to say something about the structure of space-time. Right?
So the thought is like just because it's indispensable mathematical talk, because it's doing something really important and important to the success, we don't have to cash that out in terms of corresponding to something real, to truth. Is that kind of what
no, the problem is if you bought the standard characterization of scientific realism, we ought to believe our scientific theories are true, then you have to say, okay, well, the maths involved is true if you can't dispense with them. So typically the easy road nominalists will say, well, we need a more nuanced form of scientific realism. What we're really realist about, what we really ought to believe, is the physical content of our scientific theories, the non-mathematical content, right? So when I say space-time is structured like like R4, what I really mean is physical space is the way it would have to be to make that claim true.
Right. Gotcha.
Or as Mark Balaguer puts it, the physical world holds up its end of the bargain. Right? I don't care whether there really are real numbers or not. What I care about when I'm making that claim is what space-time points are like.
Right.
And if they're holding up their side of the bargain, they're the way they would have to be to make that mixed claim about the relation between physical objects and mathematical objects true. Now, whether the mathematical components really exist doesn't matter to what I'm trying to do. So the easy roader says, look, we don't have to be scientific realists in the way that we'd previously characterised it. What we ought to be is some kind of nominalistic scientific realist. We ought to believe the nominalistic content of our scientific theories, because we've got good reason for thinking that what the mathematics is doing in our theories is expressing that nominalistic content. And that's something that it could do, whether there are numbers or not, just in a way that appealing to fictional characters can help describe. You can describe your friends to people by saying, they're like Homer Simpson or whatever. Right? You can do that without thinking, there's some object, Homer Simpson.
There's a real, yes.
So if what we're interested in is the content expressed by our scientific theories, that's the bit that we ought to be realist about. Right.
Okay, that's fascinating. So, and then come back to the underlying motivation. It's these epistemological concerns of knowledge. That how do we, if these numbers are real, how do we know about them? And so we're trying to avoid that. Can I just get to like a worry I have then in the background that might be different from the normal worries that we've been discussing with indispensability and so on. It seems even if we can get rid of mathematical talk, we're still going to have logic, for example. I mean, when we were talking about Hartree Field and how he gets rid of reference to numbers, we turn to logic and how you can sort of articulate numbers in a sense with just pure logic. But isn't there still going to be an epistemological worry here? I mean, I'm thinking, for example, claims about logical possibility that, let's take a really simple case, square circles are logically impossible, that there's no possible world where there's a square circle. So isn't there still an epistemological worry? It's like, how the hell do we know, just sitting in an armchair thinking about stuff, that in no possible universe is there a square circle? So don't we still have a worry here? Even if okay, we're not, how do we know about numbers? We're still, how do we know these huge claims about how being itself is constrained?
Yeah, absolutely. So
what keeps me awake at night?
Quite rightly, because it is one of the big problems for this kind of picture I'm trying to push, right? So if you're a mathematical fictionalist, of my sort at least, you don't think that there are numbers, but you do think that there are facts of the matter about what's true in the story of the numbers, right? So
yes.
So when I say to people there are no numbers, people say, "Well, you think 2 and 2 isn't 4?" Well, not really, right? Because I think that is true in the story of the natural numbers, and that
Yes.
story is given by axioms and so on. And then when you ask, well, what is the story of the numbers? It's the axioms and what follows from them. Okay, so then I have an issue, an epistemic issue. How do we know, not the axioms now, because I've said the axioms we've just chosen as we like, but how do I know these facts about what follows from the axioms?
Right.
And certainly within philosophy of maths, some people will push that back on the nominalist or the fictionalist and say, look, this puts you in no less of an epistemic problem than the Platonist, because actually, especially if you're doing mathematics and looking at questions of logical consequence, well, how do we know what follows from that? We give a derivation, or how do we know something doesn't follow from something else? We give a set theoretic model in which the claim, the premises are true and the conclusion is false. Now, especially that, there's an issue in the first, but especially that latter mode of finding out what follows from what seems to require us to say, okay, well, I can know what follows from what by knowing something about the sets, right? So insofar as we use sets, mathematical objects, to find out about facts of logical consequence, if we think that we have this knowledge about logical consequence, we're back in the same problem as the Platonists. So that raises the question, well, what can a fictionalist say about that, or knowledge of logical possibility, effectively?
Yes.
And how can they justify their reliance on set theory for finding out about those things?
Right.
So here, there is a bit of an act of faith, if you like. What the fictionist can say is, well, look, my use of set theory, let's say, so I use set theory to find out whether a claim follows or doesn't follow from some axioms. I can try and show it doesn't follow by finding a model of those claims in which the axioms are true and the conclusion's not true. When I find a model like that, to falsify the claim that this follows from that, so to find out something about logic, my use of that model doesn't depend on my thinking that set theory is true. It depends only on my thinking that set theory is logically possible.
Right.
So if I think my axioms for set theory are logically possible, then relative consistency tells me that anything that I can model in the sets is also logically possible. So all of those uses of mathematics to find out about logical possibility, logical consequence elsewhere, all of those uses of set theory to do that can be justified just so long as I think that set theory is logically possible. And then that raises the question, well, how do you know that? So that's the big epistemic problem, right? We have mathematical, let's say ZFC, we have our axioms for set theory. What confidence do we have for believing that those are consistent, that they're satisfiable, that there could be objects of that sort?
Yeah.
And there, I think we have to rest on actually the imagination, because, well, there's a little bit of inductive evidence. We've been using those axioms for a long time, and they've not got us into trouble. But most of our confidence in the consistency of those axioms, or in their logical possibility, if you like, most of our confidence comes from our picture of how the sets could be, and that comes from the so-called iterative conception of sets.
That's really
where we kind of have an idea of how the sets would be laid, how objects satisfying the axioms of set theory would be laid out. So insofar as we think that conception is a kind of coherent one, we think we can imagine things being set out that way. That's where our confidence that any of this stuff helps us to find out about logical possibility.
That's so fascinating. So I don't know, I'm still a little bit unsatisfied. Like there's still a claim about how reality could be and what justify. Can I try a wacky solution? I'm playing with at the moment. So I mean, coming back to Plato, right? Okay, in some sense, Plato gives us a reductionist story because he has all these numbers and all these forms and so on. But he thinks they emerge from a single entity, the form of the good, right? There's this single entity that they all emerge from. Now he places the form of the good outside of space and time, and we've got the epistemological worry again. But suppose the form of the good wasn't outside of space and time. Suppose it was underlying physical reality. Suppose it was at the core of our being. And many mystics throughout history have claimed to directly experience something like this. And viewers of this channel will know I recently had quite a profound mystical experience myself using a powerful psychedelic, discussing, is this a real, is this a hallucination? But suppose that was true, right? Suppose the form of the good that is the source of mathematical logical truth was somehow at the core of our being, as the mystics suppose. That would give us an answer to the epistemological worry, perhaps, or potentially, because this might give us sort of epistemological access to the source of these truths. That would, now, you might have other worries, you might think this sounds a bit wacky, but maybe I could put it conditionally. Put it this way, if you have a completely naturalistic, physicalist worldview, this form of knowledge, of logical possibility, of how reality is constrained, is very mysterious. If you have this kind of more mystical picture of things where the source of mathematical truth is at the core of our being, it's not mysterious. So maybe there's a point in favour of this sort of mystical conception that's perhaps not often focused on.
You won't be surprised that I'm not going to be convinced by that. And I guess one of the problems there is, you're right, you've identified a gap, something that we need to tell a story about, how we have knowledge of logical possibility. But your answer is, well, suppose we just have it. Right? Suppose we just have it. Sure, but I could say, suppose we just have it for some other reason than it's the form of the good. Suppose that's just inbuilt into us. I think what's more fruitful from my perspective is to try and look at. So there's something that we find compelling about the laws of logic. Actually, not everyone when they first see them, right? But eventually, when you've done enough logic, you start finding the laws of logic compelling. I've been reading a lot of Penelope Maddy recently on the logical must, and her story about why it is we find those laws compelling. And she says, look, we've developed those as people who've evolved in a world that roughly meets those laws, right? In rough terms, it's a world of objects with properties at the medium-sized level, and the laws, if you have enduring objects with enduring properties, these are the kind of laws that apply to objects of that sort.
Right.
So her picture is, well, look, we've been kind of honed by the world we're in to find these laws compelling. Does that mean that they've got some great eternal property of necessity about them? Well, maybe not. They just seem to us to be the right ones to use, and luckily enough, because of the kind of world we're in, they are the right ones to use for the most part. When we're not encountering vague objects or the quantum world or so on, these are the laws that work. So now I'm not convinced by the whole of Maddy's story there, but what I think is interesting there is the thought that we can kind of demystify a little bit the idea of the necessity of the laws of logic, that they somehow tell us how things would have to be in every possible world. God knows, right? But that wasn't a pun, but I'll take that. But what they do tell us is, what we can know is that they work perfectly serviceably in our world and worlds like ours, because that's the kind of world we find ourselves in. And ultimately, what we need these for is for reasoning about our world and worlds like ours. So we don't have to worry about some kind of mystical access to all the ways things possibly could be.
Yeah, so I suppose that's really interesting. So we're really coming down to foundations, aren't we, of these most foundational forms of knowledge. What do they consist in? How are they possible? Can we give some kind of deflationary account? And yeah, you've given me lots to think. I could talk about this for another 2 hours, but you've given me a lot to think on of these different ways of thinking about these foundational questions. Is there anything you'd like to share with viewers and listeners about your own work at the moment, or how people can learn more about your work, or what you've been thinking about?
So what I've been thinking about recently is an issue that comes up for me that kind of is difficult for a fictionalist. Because if you're a fictionalist, it looks like any fiction's, metaphysically speaking, as good as any other, right? So long as your axiom, you can come up with a mathematical story, come up with a bunch of axioms, so long as they're consistent, off you go, work out what follows from them. That's what mathematics amounts to. And yet, increasingly, I'm thinking there's more to it than that. There are better and worse choices of mathematical axioms. So in particular, I'm thinking about set theory, for example.
Right.
There's different consistent set theories, that consistent extensions of our standard set theory that add different axioms that answer questions in different ways. So questions like the continuum hypothesis, which is a question about how many different sizes of sets of real numbers can you have. Right. Now, it turns out our standard axioms for set theory don't answer that question. If you it's coherent to add axioms that give one answer and coherent to add axioms that give a different answer. So if you're a fictionalist, if you say, I don't believe in real numbers, it looks like you shouldn't worry, right? You should say, well, each of these set theories has its own story about its real numbers, and each of them is fine in its own right. You know, you can tell this story, that story, another. And yet I kind of want to say no. There ought to be a right answer to that. So I'm trying to pursue the question of whether it makes sense to say that there's objectivity in mathematics, even if you don't really believe that these objects exist in a real sense.
Right. Oh, I'm looking forward to seeing where you end up with that. Mary Leng, thank you for making my head hurt. I've really enjoyed the conversation.
All right. Thank you very much, Phil. Really enjoyed it too, but I better run.